Okay, so today I'm going to be talking about a few features that we're working on at Intel, and mostly focusing on features that are already, under progress and are going to be landing in the next couple of releases. And at the end, I don't know if I'll spend too much time on it, but there's a few features that are just starting up development and are interesting, but we don't have a target release for them. And these features, while we're planning on getting them into a specific release, it's still subject to change depending on time schedules and implementation. So the first one it's been in progress for a while, but it's already started to land for Lustre 2.7, which is the current development release and is still accepting features until the end of October. So dynamic LNet configuration, and it's mainly focused on being able to configure Lustre and change the Lustre routing configurations and things like that after the system has already been set up. The current implementation is somewhat static in that you can't add and remove new routes and new interfaces after the system has been mounted, because it gets the Lustre network configuration from the module parameters. And since this is the Lustre administration and developer conference, I've added in some actual how to use things here. So it's intended to be used like the route command, so you can route add, route del, and so this one, the LNet control command is being added, and it adds new net add, and you can add in a new network on a specific interface. So a network would be, O2IB2 or something like that on the IB2 network. You'll be able to tune things like peer credits on a per internet interface basis, which you can't do right now. So that if you have different classes of networks, you can tune them more fine-grained than you can do today. I'll show you on the next page. The other main improvement from the dynamic LNet config is that you can read the LNet configuration from a file, and so that allows you to have larger LNet configurations than were previously possible as module parameters, because there's a 4K size limit on a module parameter in the kernel. So it will allow reading from a YAML formatted text file at startup, and you can also generate the YAML configuration from the current. If you go through and you set parameters and you configure interfaces by hand on a sample system, you can generate the configuration file from the current network configuration. You can use the LNet control net show or the route show commands to generate the specific YAML format. And as you can see, I don't know if people are familiar with YAML, it's a very simple text format that allows both human, it's pretty human readable, but it's also parsable from scripts, and it's not just a random blob of text that needs to be, complex parsers. So there's YAML parsers for shell and for C and for Python and Perl and everything like that. So it's relatively easy to interface to other tools. And so this has been under development for a while, but it's gone through a series of revisions based on feedback from users at Livermore and things like that, or not users, but system administrators, to make it more in tune with how they're configuring Lustre and their Lustre routing. The next feature that I thought that, well, we're working on is Lustre file system checker. And as I was going back through some of the older presentations on, actually one thing I didn't mention here, on the bottom of my slides, for each of the features, there's a link to, you know, previous, some other documentation and things like that on that specific feature to get more information about it. I can't, you know, describe every feature in specific detail. LFS check, I thought I'd go back a little bit because the presentations that that have been made on LFS check, while they talk about the theory of, you know, how it's being implemented and things like that, they don't really describe how people can use it. And I thought, since this is the administrator conference as well, I thought I'd throw in a bit of you know, how to get started using LFS check. And so going back through the currently supported releases, what's been added is this L-control LFS check start and LFS check stop. And in the 2.4 time frame and 2.5, what this allows you to do is check the local on-disk consistency of the MDT. And if you've done a backup restore, like a file level backup restore, which, you know, didn't work in the Lustre 2.1 through 2.3 time frame, the LFS check in 2.4 implemented the object index scrub, and so it goes through the whole file system and verifies the file identifiers that are stored in each inode and matches that against the object index files, which are Lustre specific. And the backup restore wouldn't restore these files properly, but they get regenerated by LFS check on a running system, so that if it detects inconsistencies when it starts up, this automatically gets run. You can also run it manually and you know, get your system back into a working state. And then in the 2.5 time frame, we added in the LFS check 1.5, and it added in the -T namespace option, which lets you verify the FIDs that are stored in directory entries, which if you've done an upgrade from you know, Lustre 1.8 or 2. If you upgraded from Lustre 1.8, the file identifiers aren't stored in the directory entries, and so you have to do extra disk lookups. And so if you're doing ls-l, it actually puts quite a bit of higher load on the MDS. And so if you do the namespace scanning, you know, it checks for those directory entry FIDs. It will also verify and or repair the link extended attribute. So as one of the earlier presentations showed, if you have the file identifier from an error message, or from, if you've ever looked on the OST with debugfs, it tells you what the parent FID is on a given OST object for, you know, if you need to figure that out. You can use the FID to path command, but if the link extended attributes aren't present due to upgrade or due to corruption or something like that, this will repair those link attributes and allow the path generation to work again from a given FID. And so on the bottom is just a little diagram that says, you know, for a given directory, if you have some files, foo and bar, inside that directory, what gets added in is the orange FIDs get added into the directory entries, so that if you're doing ls-l, you know, you have that on the client. You can do the lookup by FID directly. If you've done a backup restore or the upgrade from 1.8, it will store the FID in the inode. This is a hard linked file, by the way. So two names pointing to the same entry. You'll add the FID attribute onto a given file, and then in the link extended attribute, it has a back pointer to what the parent directory entries are for using in the directory path creation. In the 2.6 release, which was just done a month or two ago, we added in the LFS check phase 2 feature, which is verifying the consistency between the MDT layout and the OST objects. And this allows you to detect objects that are unreferenced on the OSTs, for instance, or if they have multiple references. And then you can, recover if there's, because of, let's say, you run E2FS check on the MDT and there were some files that were corrupted and erased. Now you have these entries on the OSTs that are never being used anymore. And so you want to be able to detect them. So it goes through the entire, as you're scanning, it's the same scan, by the way. So as we're doing these different phases of LFS check, they're essentially building new functionality. You scan your MDT a single time, and we're adding in layers of checks on the metadata that you're reading from disk. So it doesn't do multiple passes through your MDT. It's all done with a single, mostly linear set of disk reads. And so it's a one-pass algorithm to minimize the disk I/O. And so in phase 2, we look at, on every inode that's being read, we look at the law of EA and the layout, and we check every OST object. And then so the MDT does an RPC over to the respective OSTs to verify that that object exists. The OSTs, when they start up their scan, they generate a bitmap of all the objects that are existing locally, and then they keep track of all of the objects that get referenced during the scan. And so by the time they get to the end of the scan, they know if there's any objects that existed at the beginning that were never referenced by any MDT object, and so we can figure those ones out as being orphans. As well, at the same time, this allows you to validate and repair the user and the group ownership of the OST objects. So this allows you to repair quota, which was a problem that was mentioned earlier. So in Lustre 2.6, it will repair the quota on the OST objects so that you're back in a consistent state. It also verifies the parent FID on the OST object so that, for instance, if there's two MDT files that reference the same OST object for some reason, then if one of the MDT files gets deleted, you would delete the OST objects, and now the other file is left without any data. I mean, it's a bug in the first place that you should get these two references to the OST object, but at least the LFS check phase 2 will detect that and repair the multiple links by making a copy of the file. So this one, in 2.6, it adds in here at the bottom 2 extra options into the LFS check start. -A means start the LFS check on all of the respective MDT and OST targets, so you can launch it from MDT 0, and it will run the scan on all of the servers in the file system, and you don't have to start it individually. It adds in the layout type checking, and it adds in an extra option if there are OST objects, like if you have an MDT file that's referencing an OST object that doesn't exist for whatever reason, it will create an empty object. It doesn't do that by default because it's an object that has no data in it, and it would essentially hide the error. So, I mean, if somebody's accessing their file today, you'll get an error back when you're trying to read that file, and they'll realize, hey, my data is gone. Right? If you create these objects, it makes the file system consistent, but might hide an error from some application, and so it doesn't do that by default until the administrator asks for it. And then the other feature that was added is the ability to do scanning on ZFS backend file systems, which wasn't present in Lustre 2.4 and 2.5. So for 2.7, we're getting near the end of LFS check development. The phase 3 feature is implementing the scanning for consistency for D&E features, so cross MDT directories and striped directories, which are also being implemented in Lustre 2.6. And so the LFS check is verifying the consistency of those things. Of course, if you have cross in D&E, if you have cross MDT hard links, entries, the directory entry on one MDT is pointing at an inode on a second MDT, and then you have a back pointer from that MDT, like the ... entry of the directory is pointing back at the parent, and the link EA is pointing back at the parent, and you want to make sure that those two pairs are consistent. And the stripe directories also have a directory structure. There's a master. I think there's a diagram in a next under D&E that shows how the stripe directories are structured. But in LFS check, so we add in this -t all, which means add it, do all of the different LFS check scans at the same time. I mean, in the previous version, it was just you have to say -t namespace, -t layout, and all of the messages, like what's getting repaired by LFS check, is going into the kernel debug log, and so you want to turn on, if you're running LFS check, you want to turn on the LFS check debug logging, and dump the log when you're done, and you can get the status. There's there is a dry run option when you're starting LFS check, which means do the full scan but don't do any repairing, and then you can run get all of the logs and see if there's any inconsistencies that would need to be repaired. Actually, the other thing I didn't mention, there's also a speed limit, so you can put in say only scan 1,000 or 5,000 objects a second, so that you're not impacting normal metadata performance. So it is pretty fast. I think it's depending on your hardware, 50 to 100,000 inodes per second, because it's mostly just doing a local disk scan. But that can impact your metadata performance. And there's some proc files, mdd dot whatever MDT number, LFS check layout, and a separate one called LFS check _ namespace, and you can watch those to see how fast it's scanning, if it's repairing objects or finding inconsistencies. It just gives you an aggregate of the statistics on the performance. And there's a presentation, and the design and things like that are available online. So D&E is a feature that's been under development also for quite a while, and it's also nearing completion of development. In Lustre 2.6, it got the stripe directories feature, which allows you to have scale. Like in 2.4, the D&E allows you to have multiple MDTs in a single file system. And so in the 2.4 and 2.5, the intent is that you can take a single file system and split it up sort of at the directory level. So one user gets put on one MDT, another user gets put on a different MDT, and you can split up load sort of at a coarse grain level of this whole directory subtree. In 2.6, the stripe directories allows you to split up a single directory, so that if you have some users, they like to dump 10 million files in one directory or 100 million or whatever they would like to do. And so this allows you to scale the performance of a single directory. And it essentially just generates a name hash based on the file name that's being accessed, and then picks whatever MDT that will land on. And there's a per directory, like it's the same as files conceptually. There's a layout per directory that says, is this a striped directory? How many MDTs is it striped across? What hash function is it using? And so you can pick on a fine-grained level, for directories that are large that you want to stripe across multiple MDTs. And so in 2.6, this feature landed. It's still in a preview stage, so it works. It's not necessarily expected to be 100% bug-free, but it's definitely there for people to test out. There's still some work ongoing that will land in the 2.8 time frame, which is asynchronous commits. So right now, the stripe directories and remote directories, they're synchronous, and they need 2 sync intervals in order to commit. So they're really expected to be used for, splitting up trees at a high level, and not for like individual directory entries being split across MDTs. And so to use the stripe directory or remote directory features is using, you create an next, additional MDTs as you would a MDT 0. You obviously have to specify the index to be some non-zero value, MDT 1, MDT 2. And then once you mount those MDTs, you can, like you do with LFS set stripe, you can do LFS make dir and give it a -I for the index on which you want to create a directory. If you want, you can give it a stripe count and say that, this new directory is located on MDT 2 and it has a stripe count of 4, and then you'll split all of the directory entries across 4 MDTs. And then deleting remote or stripe directories is just rmdir. One of the limitations that exist today is that rename and hardlink don't work with stripe directories, and you can't do hardlinks across MDTs yet. So that's something that's being worked on for Lustre 2.8. It's because that you can't do the renames or hardlinks. It returns exdev, but user space tools treat that as essentially meaning it's on a separate file system. And so if you do MV, it will actually just copy the tree over, which is not ideal, but at least it works. And there's a tool in the Lustre 2.6 LFS MV, which will move the inode over and keep the same OST objects. It creates a new inode that references the same OST objects, so you don't have to do a data copy. But because it's not, it creates a new inode with a new FID. It's not POSIX compatible, so we didn't want to expose it using the regular rename command. But if you use LFS MV, you can migrate, a user's directory tree over to a new MDT or something like that. And there's also, again, some more resources on these, finding out about these features. And so this is the feature async commit, which I'll just go through quickly because we don't have much time. It's essentially allowing the operations that are spanning multiple MDTs to commit and be recoverable in a consistent manner without requiring a sync on both ends of that operation. And so, this will mean that, you can do hard links, you can do renames. It will go quite a bit faster in 2.8. And so we're sort of holding off declaring this as a GA feature until this feature is completed. So data on MDT is another project that has sort of started implementation. I don't have, so this one has a version 2.x. We don't know when data on MDT is going to be finished implementation. It's just in the early implementation stages today. And the goal is that you can store small files directly on the MDT. And the main benefit here is that instead of having to look up an inode on the MDT and then get it back to the client, and then the client has to go to another OST to look up the inode there, and then come back, and then another RPC to read the data or write the data. This is essentially, it's going to gain performance based on just fewer RPC round trips, which is a big deal, especially for small files where you're not transferring a lot of data. The other benefit is that MDT storage is typically, IOPS oriented. It's on SSDs or SAS, 10K, 15K devices, and so reading, a few kilobytes is going to be faster, and it's not, be in the queue behind, gigabytes of other user data that's, queued up on the OSTs. So there's a number of different areas that it's going to gain performance. The other one, I guess, is RAID 5.6. On the OSTs, you're not going to have big read, modify, write penalty for, reading a 4K chunk where there's a 1 megabyte, RAID stripe. And the space is going to be managed by quota on the MDT. That's something that has to be implemented still. But you want to, because the MDT sizes are limited in terms of how much space they have, you don't want users to just say, well, I want my files all to be fast and store them all on the MDT. So there has to be a quota limit there. And it is really limited, expected to be limited for small files. So typically, a megabyte or 512 kilobytes or something like that. The administrator will be able to specify a limit, and the users can specify a smaller limit if they want by setting the stripe size, and it will say, okay, you can only have 1 stripe worth of data before it'll return EFBIG. And in the initial implementation, you'll just get an error back if you try to store a bigger file there on an MDT. In later versions, the intent is that if you start by writing a small file on the MDT and it gets too big, it will migrate it over to an OS. Is you have a round trip just to look up attributes on the MDS, and then you have to fetch your attributes. Let's say ls minus l, you get the size, or if you're doing a read or write, a truncate. All Lustre layouts. This has to be specified at file creation time, which is a little bit unfortunate. File, then store it on the MDT, because you pick the layout at the time the file is opened and you don't know how much data is coming. And so this either has to be done with LFS set stripe to create new files, or there'll be a default layout on the directory that says this is a directory that's going to contain small files. And so it'll be selected through LFS set stripe parameter, and it'll give you a stripe pattern, which up until now has always just been RAID 0, right? It's just a default and nobody's ever used it. But you'll be able to specify that the MDT stripe pattern means that the data is only going onto the MDT. Another area that is ripe for improvement is single client metadata performance. In the past, this hasn't been a a big limitation because, you know, you only had 2 or 4 or whatever cores on a single client, and you know, you just scale out by having lots of clients. And in modern systems, you know, you have 16 or 32 cores on a single client, and now there's a bottleneck with a single client metadata performance. And there's, you know, it was described earlier today about the architectural limitation of Lustre with having multiple metadata RPCs that's due to recovery. And so this work, which is in sort of early prototype, is allowing the one client to have many, you know, RPCs in flight and still be recoverable. And so there's some early, you know, performance results from this, and it's showing that, you know, you're getting a pretty decent, once you're scaling up past 2 threads, you know, where you would bottleneck before on the client, now it's scaling up about 4 times that from a single client, which is pretty good improvement. I mean, you won't obviously see this if you're running 8 or 16 clients running at a time. You know, you end up being limited by the MDS performance anyways, right? I mean, in some of the graphs I saw, MDS performs about 100,000, 150,000 per MDS, right? But so at least we're getting up to being able to load the MDS better from a single client. Another area that's just starting out in development is layout enhancement. And so this is intended to provide the framework for RAID 1 replication, and also allowing you to have an essentially dynamic layout, which is a long-standing request, to allow Lustre to, you know, scale the striping of a file based on how big the file is, right? And so that lets you keep, you know, the striping on a single OST for small files, so you don't get a lot of overhead for small files. But if you have a big file with lots of clients accessing it, the striping will grow as the file grows. And you know, this is, you know, again, an example. It was nice and animated in my presentation. I guess this is the PDF version, so it's not animated. But it's just saying, you know, on a mirrored file, essentially what you'll be able to do is either take an existing file and add a replica to it, or at a later stage, you could create it as replicated in the, like mirrored in the first place and write to them in parallel. The striping count is not required to be the same on both replicas, so that you could have something, let's say, one replica is on flash on a, you know, local, you know, high-speed cache, and then you stripe it out to, you know, your disk-based OSDs at a different stripe count, because you have more disk-based OSTs than flash OSTs or something like that. And then, you know, at some later point, you can delete the flash replica, you know, as your flash is running out of space. Similarly, dynamic striping, you know, it says you start off with one object. Maybe once you hit 32 megabytes, you get, you know, 4 stripes. And once you're after a gigabyte, you know, you stripe over every OST that you have, right, until the end of the file. And I think that's it. Any questions?
Andreas, did you analyze it worst case for multi-slots feature? Like if we enable multiple modification RPCs from single client, we will increase MDT load dramatically, and total latency for operation between different clients will be increased. Like one client will send 5 RPCs, it will be executed, and next client will be wait this time until execute own requests. But before multiple slots, you will have execution request one by one.
Yeah, I mean, it's, you know, the OSTs already allow 8 modifying RPCs at a time, right? And so it's not expected to be any worse than the latency of one client sending many requests to an OST.
I don't say about OST, about MDT.
No, I know, but I'm saying that the OST already allows 8 modifying requests, and the MDT already allows 8 non-modifying requests at a time.
But OST not CPU-bound service, but MDT is CPU-bound, so it is very, very different between.
Yeah,
I agree about multiple slots for OST, it should be good, but for MDT, I think we should be make more testing about.
Yeah, it's still going to be tunable, right? So you can specify the number of slots, right? And you know, ideally there's going to be some sort of dynamic load balancing by the number of RPCs, or you could put in NRS policies that will make it, you know, optimized by whatever, you know, QoS. There's already the token bucket filter NRS policy, which allows you to load balance by user or by group and by job ID and a number of different policies. And so, you know, for the workloads where this is impacting it negatively, you can limit the rate, but I think it's definitely in many workloads, it's going to improve the performance because you do have so many cores on each system today. So I think it will be a net win.
Many modification RPCs may say many threads will be staying waiting different logs from different clients. So it is question.
Yeah.
Second question about data on MDT. Per your slides, you will have increased numbers of RPCs to the MDT. Like in traditional scheme, you will be sent one RPC to the MDT just to open a file, maybe a size modification and layout. But with size on MDT, we will overload MDT with data requests.
Not really, actually, because with data on MDT, you get size on MDT for free, right? Because there's only the one object.
Free. You will have seek for disk. If you have a non-flash disk, you will be additional seek with access to data.
No, because the size will be stored in the same inode as
size, yes, but not about data.
No, it's true, but you know,
access to data will be it's additional seek on disk.
I think most MDTs will be moving to flash anyway, right? So you know, storing the seek, I agree, it can hurt the performance. Again, it's going to be tunable, and not, I mean, any of the current MDTs will probably not be suitable or not be configured correctly because they won't have any extra space, right? Typically, MDTs today don't have enough space to store a lot of data on them. So this will have to be something that is enabled by the administrator after they've, you know, planned their system, right, to have enough space on the MDT. And it's probably not going to be enabled by default. So
it is a question about ability to disable this and use traditional scheme.
Yeah. Thank you. Okay. Thanks.